Good morning, good afternoon, and good evening. We got it right this time compared to the last video. Hopefully you followed that along. Did it on purpose, if you will, just to make sure that everybody's on their toes. So here we go. Today we're going to be doing gases worksheet number 2. Before you watch this video, of course, you do need to watch the prior video, and that is gases worksheet number 1. That's absolutely critical. All right, so I'm just going to highlight and do a quick little overview of some of the equations that we'll be covering in this worksheet here. So number 1 is this equation right here, and I'm going to highlight it in blue. This is actually called the combined or the general gas law. All right. So that's P1 V1 over T1 equals P2 V2 over T2. And P stands for pressure, V stands for volume, and T stands for temperature. So this is a comparison right here. This is a comparison under one set of conditions as opposed to another set of conditions. And then what we have is the mathematical relationship to convert temperatures, and that is converting degrees Celsius to Kelvin or Kelvin to degrees Celsius. Today we'll be focusing on converting degrees Celsius into Kelvin. How do we do that? We add 273 to the degrees Celsius temperature to arrive at the Kelvin temperature. Notice that there is no degree symbol on the Kelvin. All right, the next equation is Graham's law. And that is going to be here in the orange. I'm going to highlight that in orange. This is called Graham's law. I'll write that out here for you. That's Graham's law. That's Graham's law right there. Right? This is comparing the rates or speeds of two different gases at the same temperature. So it's absolutely critical that it's at the same temperature. So the rate of gas A compared to the rate of gas B is equal to a square root of the inverse molar masses or densities. Basically, what this says here is the at the same temperature, low molar mass, low density gases travel fast, and high molar mass or high density gases travel slowly. All right. The next equation is going to be PV equals nRT Pivnert, and that is called the ideal gas law. That is the ideal gas law. That's right. And then I'm going to use another color here to designate the ideal gas law constant. It's a slightly different yellow. This value right here with these units goes and is replaced with R. R is the gas constant. So in the ideal gas law, we have P for pressure, V for volume, R for the gas constant, T for the temperature, and then N is the amount of gas in moles. So that's absolutely critical. Make sure that you watch the stoichiometry videos before you do this so that you know how to do that as well. All right. Then over here, we have 1 atmosphere equals 760 millimeters of mercury equals 760 torr equals 14.7 pounds per square inch or PSI. Pressure conversions. These are pressure conversions. That's what those are right there. Okay. So without further ado, we're going to go through 6 problems here today. And again, make sure that you have watched gases worksheet number 1 prior to attempting to watch gases worksheet number 2. All right. So here we go. A gas in a vessel occupies 850 milliliters. I'm assuming that you know something here, and that milliliters is a volume. It's the first volume that we're coming across. I'm going to say it's V1. And then I have 2.2 atmospheres. Atmospheres is a pressure. So that's pressure 1. This volume 1 and that pressure 1 goes together. And then it says, what's the volume of the gas? So that's going to be V2. That's what we're solving for. That's what I don't know. Of the gas, if the pressure is changed to 6.3 atm, that's going to be pressure 2. All right, so because we have two volumes and two pressures, or actually we truly actually only have two pressures. We have one volume, but we're solving for the other volume. Therefore, we need a gas law that's a comparison. The only gas law here that is a comparison is the combined or general gas law. PV over T equals PV over T. So I'm going to rewrite that down here. P1 V1 over T1 is equal to P2 V2 over T2. And then we're going to ask ourselves a question here. Is there temperature mentioned in this problem? There is not. Temperature is not mentioned in this problem. Because of that, that means that temperature is going to be constant. So I'm going to cross out the temperature. Okay. When you have a pressure-volume relationship at the same constant temperature, that is actually a Boyle's law problem. So this is a Boyle's law problem right now because temperature is being held constant. The combined gas law, just as it is written right here, is a combined gas law between Boyle's, Charles, and Gay-Lussac's law. So the combined gas law can be used for Boyle's law, which it will be here when temperature is being held constant, Charles' law, and Gay-Lussac's law when pressure and volume are held constant at different times. So what we're going to do is we're going to plug directly into P1 V1. We're going to find where our P1 is. That's 2.2 atmospheres. That's 2.2 ATM. And that's the P1. And then I'm going to plug into here, and that's V1. The V1 is 850 milliliters. At 850 milliliters, right there like that, is equal to P2. The P2 is 6.3 ATM. And then V2 is what we're solving for. V2, just like that. All right, so what we're going to do is we're going to rearrange this equation and solve for V2. That means we need to isolate V2 all by itself. That means that we're going to divide both sides by 6.3 ATM. That will isolate the V2 by itself. And what you do to one side, you have to do to the other side. So 6.3 ATM. When we do this, you should see that the units of atmospheres cancels out. I'm left with units of milliliters. That is most certainly a volume, so I'm really quite happy with that. When we do these problems, we're going to make sure that we have the correct number of significant figures. And in order to do that, what we're going to do is we're going to look at this. This is 1, 2 significant figures, 2 significant figures. This is 1, 2 significant figures. That trailing zero does not count because there's no decimal at the end of the number. That's 2 significant figures. And then 6.3 has 2 significant figures. So I'm going to plug into my calculator 2.2 multiplied by 850 divided by 6.3. That's 2.2 times 850 divided by 6.3. So let's plug that into the calculator. 2.2 times 850 divided by 6.3. And I am going to get my new value here. All right. And that's going to be my volume 2 that's in my calculator is 296.825. And let's see, we need to round this to 2 significant figures. That's 1, 2 significant figures. I'm using that 6 for rounding. I'm going to add 1 to the preceding digit. That 9 becomes a 10. I'm going to add 1 to the next preceding digit. That 2 becomes a 3. So the number is actually 300. But that only has how many significant figures? 1. If I place a decimal here at the end of that 300, like in this case right there, that would give me 3 significant figures. And neither one of those is correct, so that's not going to work either. So what we're going to have to do is we're going to have to put this in exponential notation. So it's going to be 3.0 times 10 to the 1, 2 places. So that gives me my exponent of 2. And then my units are milliliters. And that is my volume. I'm going to circle that. That has 2 significant figures. Perfect. I think you guys are looking fantastic. We have done the very first problem here. So now let's cruise on to problem number 2. Problem number 2 says a sample of gas at the following conditions, 150 milliliters and 740 torr. What is the pressure if the new volume is 360 milliliters? So what we're going to do is Gonna label these milliliters. That is a volume. That's volume 1. Torr. That is a pressure. That's pressure 1. What is the pressure? I don't know. That's the second pressure. I'm gonna say that's a question mark. And this next one here is volume. Milliliters is a volume right there. So just like what we did before, we're using the combined gas law. So I'm going to slide this on up so I give myself a little bit more real estate space here on this page here. So I got P1 V1 over T1 is equal to P2 V2 over T2. And just like on the previous problem, there is no mention of temperature in this problem. So I'm going to cancel out the temperature because it's being held constant. And then this is actually a Boyle's law problem. So let's plug in these numbers. P1 is actually equal to 740 torr. V1 is equal to 150 milliliters. And P2 is what we're solving for. I'm just going to write that as P2. And V2 is equal to 360 milliliters, just like that. Fantastic. The number of significant figures that we have, this is 2 significant figures right there, and this is 2 significant figures. Remember, trailing zeros in both of these cases without the decimal don't count, and this is also 2 significant figures. Trailing zeros without the decimal doesn't count. I'm going to isolate this P2 right here, so I'm going to divide both sides by 360 milliliters. 360 milliliters. You should see that that actually cancels out this right here. It cancels out the milliliters, and I'm left with torr, which is a pressure. So I'm going to plug this into my calculator, 740 times 150 divided by 360. So 740 times the 150 divided by the 360. And I'm going to get in my calculator, pressure 2 is equal to 308.333. Now I'm going to use 2 significant figures. It's the least number of significant figures that I have in this problem. So that's going to be 1, 2. I'm rounding with that 8. I'm going to add 1 to the preceding digit. So this 0 becomes a 1. So that will get me 3, 1. Now, this number is 308. I need to maintain that approximate same number here in the hundreds column. So therefore, I need to add that 0 at 310. This number with the 3 and the 1 has 2 significant figures. That 0 does not count because there's no decimal on the end of it. The units that did not cancel out, that was torr, and that is torr, and that is a pressure, so that is pressure 2. That is my answer, 310 torr. Perfecto. You guys are doing a fantastic job. And we have another problem to do. So we're going to slide this on up here and so that we get the real estate necessary to do this problem. Number 3. Number 3 says calculate the temperature. Calculate the temperature. So that is our question. If the new conditions are 50 mils and 1.5 atm. So milliliters is a volume. This is a temperature. And atmospheres is a pressure. Notice that I labeled all these as ones because they all go together. And the original conditions are 550 milliliters, 22 degrees Celsius, and 2.5 atmospheres. This milliliters is a volume 2. This degrees Celsius is temperature 2. And this atmospheres is pressure 2. All right, so what we're going to do is we're going to write the combined general gas law. That's P1 V1 over T1 equals P2 V2 over T2. This is the general or combined gas law, and this is the law that we're using here on this particular problem because we do have everything we need. Now, we're calculating the temperature, that's T1, so this is what we're solving for right here. So I'm going to plug in the P1 and the V1. The P1 is in atmospheres, and that is 1.5 atm. And then the V1 is 50 milliliters, that's 50 milliliters, just like that. My T1 is what I'm solving for. I'm just going to call that T1. And then my P2 is where? That's my 2.5 atmospheres, 2.5 atm. And then my V2 is right here at 550 milliliters. And then my T2. Well, before I plug in the T2, I need to make sure that T2 is in degrees. This is in degrees Celsius. I need to make sure it's in Kelvin. So I'm going to scroll this right up to the top of this worksheet here. And I had this equation here written down. And this is the equation that we're going to use for this particular problem. It's 22 degrees Celsius plus 273 is equal to the Kelvin temperature. So I'm going to have my 22, add the 273, and I'm going to get 295 Kelvin. This is going to be my temperature because I'm using this conversion with temperatures. So I'm going to scratch out the temperature that is written down here. This is 22 degrees Celsius, but it's been converted to 295 Kelvin. Hopefully you followed that along. So I'm going to place that in here, 295 Kelvin. Just as a note, anytime you are using a gas law and you're doing a gas law problem, you must have the temperature in Kelvin. It's just a must. And the reason for that is that there are no negative Kelvin units, no negative Kelvin values, rather, as compared to degrees Fahrenheit or degrees Celsius, of which there are negative values. And we cannot have negative values. That's not a good thing. All right. So we want to solve for T1. How do we do that? We cross multiply. So I'm going to say T1 times 2.5 atmospheres times 550 milliliters is equal to 1.5 atmospheres times 50 mils times 295 Kelvin. So that's what we're going to write down here. Okay. So I have a T1 times 2.5 ATM times 550 milliliters is equal to 1.5 atmospheres times 50 mils times 295 Kelvin. And again, our ultimate goal here is to solve for this T1. So I'm going to isolate that and divide both sides by the pressure and the volume here of 2.5 ATM, the 550 milliliters, and we're going to do the same thing to both sides. 2.5 ATM, the 550 milliliters. Perfect. You should see that this cancels out here. This cancels out here. The atmospheres cancels out. The milliliters cancels out. And what do I have left? Kelvin. And I am solving for a temperature. That is correct. So what we're going to do is we're going to plug into our calculator 1.5 times 50 times 295 divided by 2.5 divided by 550. Okay. So really simple, keep it simple, stupid rule. And that is if it's in the numerator, you multiply. If it's in the denominator, you divide. So I got 1.5 times 50 times 295 divided by 2.5 divided by 550. And the number that I get for T1 in my calculator is 16.0909. Now I need to look at significant figures. This number 1.5 has two significant figures. This number 50 has one significant figure because that trailing zero does not count. This 295 after converted to Kelvin has three significant figures. 2.5 has two significant figures, and this 550 has two significant figures. So the fewest number of significant figures I have is actually 1. So I'm going to round this to one significant figure. I'm rounding with that 6. It's 5 or greater. I'm going to add 1 to the preceding digit. That will give me 20 Kelvin is my temperature for my T1. All right, 20 Kelvin. Perfecto. All right. Now, what we're going to do is we're going to take a little quick station break from our sponsor, and we're going to thank our sponsor. Who is our sponsor? The sponsor is the Crazy Hat Chemist. And your sponsor would like to say thank you very much. In addition to that, you know what to do. Please watch the video in its entirety. We need as many views as possible. We need you to subscribe to my YouTube channel, and we need you to give a thumbs up and to like it and send me some comments. You're confused about something or you want some more help on a problem, then shoot me a comment and I'll be happy to help you out. It's a guarantee. I always answer my comments, and sometimes those comments are getting out of control, I've noticed, but I do answer them. So please like, subscribe, and or subscribe, then like, and throw some comments down in there about how much you're appreciating what you're learning here in the real chemistry world. All right, let's go on to the next problem. By the way, we are halfway done with this worksheet, so we're going to do problem number 4 here. Fantastic. Problem number 4. Problem number 4, it says the following: which gas is faster and by how much in comparing carbon dioxide, that's CO2, and carbon monoxide, that's CO, at the same temperature. This is actually key and critical. Okay, so the first thing that we're going to do is we're going to look on our periodic table and we're going to find the molar mass for carbon dioxide and carbon monoxide. Here is carbon for, let's fold this over just a little bit so that we can get the carbon and the oxygen visible. There's the carbon, there's the oxygen, 12.01 and 16.00. Now you might have a different periodic table and you'll just have to use the numbers that are on your periodic table and the appropriate rounding. However, you should be able to get something similar to this. The molar mass for carbon dioxide using my periodic table would be 44.01 grams per mole. And the molar mass for carbon monoxide is 12.01 and the 16. And that would be 28.0 grams per mole. Hey, by the way, I do have a separate video that covers how to calculate molar masses of formulas and compounds. So check it out. All right, so the question is, which gas is faster? So what we're going to do is we're going to compare the molar mass of carbon dioxide and the molar mass of carbon monoxide and figure out which number is the smaller number, which has the lower molar mass. Carbon monoxide has the lower molar mass. So lower molar mass or density is the faster gas. So which is the faster gas? Carbon monoxide. Bingo. So that's the first answer. Check, done that. Now we're going to figure out how much faster carbon monoxide is compared to carbon dioxide at the same temperature. And that is dealing with Graham's law. So I'm going to scroll right back up over here. And this is Graham's law. I'm going to plug into this rate equation. So we're going to scroll this right back on up here. Here we go. So the rate of the faster gas, in this case is carbon monoxide, over the rate of the slower gas, carbon dioxide, is equal to the square root of an inverse molar masses. So that means that inverse is the carbon dioxide molar mass will go up here at 44.01 grams per mole. And then the carbon monoxide's molar mass will go right here at 28.01 grams per mole. Got to write the 1 right there. There it is. Okay, so what we're going to do is we're going to plug this into our calculator, and that is 44.01 divided by 28.01, and then we're going to take the square root of that. Okay, we're going to get a number. Don't forget it's about taking the square root. That's essential. 1.253484967707. So we don't need to include all those numbers here. This number has 4 significant figures. This number here has 4 significant figures. So I'm going to round this to 1, a 2, a 3, a 4 significant figures. I'm rounding with that 4. So the number is 1.253. Okay, so carbon monoxide is 1.253 times faster than carbon dioxide at the same temperature. So this is what we're looking for right there. That is a thing of beauty. Okay, we're going to scroll this on up. We got two more problems to do, so let's scroll this on up here. Here we go. Awesome. Hey, just a quick shout out to our sponsor again, the Crazy Hat Chemist. He's supporting all this financially with all the videos that you've been seeing. I've got over 770 videos so far. So if you want to learn chemistry, this is the place to come and the place to learn. So check out all my videos. I got videos in general chemistry, of which this is a video of. I got videos in honors chemistry, and I got videos in advanced placement chemistry. They're all in playlists, and to boot, I actually have some videos on how to cook. I'm going to be making a pretty good cooking video here pretty soon on how to make some homemade milk. So you'll have to check that one out sometime. All right, so let's do number 5. It says, what is the density of carbon dioxide at STP conditions? Okay, so here we go. We need to know the density equation for gases. Density is equal to PM over RT. Now, this is a very simple equation. This is actually derived from the ideal gas law. So the ideal gas law is PV equals nRT. It's actually a derivation of that. So P is for pressure, M is for molar mass, R is the gas constant, T is the temperature. So the first thing that we do here is we plug in the gas constant. And the gas constant was given to you at the top of this sheet of paper. That's 0.0821 liters, atmospheres, moles, Kelvin. I know there's not a lot. I know there's just one single number and there's 4 units in there, but that is the gas constant. That was at the top of the sheet of paper. Now what we're going to do is we're going to plug in the temperature. The temperature under standard temperature is actually 273. That's the temperature that we use for converting temperatures. So that's not so bad. And then the standard pressure is 1 atmosphere. Oh my goodness, that makes it really nice and easy. Now, M is for the molar mass, and it is carbon dioxide. We just happened to calculate the molar mass for carbon dioxide in the previous problem. It is 44.01. So that's 44.01 and units of grams per mole. So I'm going to make sure that the units cancel out as is appropriate so that I get units of density. Density is a mass divided by volume. So let's see if that is true. So the atmospheres cancels out. That's good. The Kelvin cancels out. That's good. And the moles cancels out. And that is good. In the numerator, what does not cancels out is grams. That is a mass. In the denominator, what doesn't cancel out is liters. And that's a volume. That is also good. Okay. All right. This is a definition because it's at standard temperature and pressure. This is a definition because it's at standard temperature and pressure. And then we'll say that this is a constant. So we'll say that that's an infinite number of significant figures. So the only one that I really have to worry about here is this molar mass, which has how many significant figures? 4 significant figures. So my answer is going to have 4 significant figures. I'm going to plug this into my calculator. That's 1 times 44.01 divided by 0.0821 divided by 273. So I've got 44.01 times 1. That's that same number. 0.0821. I'm going to divide by that. And then 273. I'm going to divide by that. And I'm going to get 1.9635662 in my calculator. I'm going to round that to 4 significant figures. That's 1, that's 2, that's 3, that's 4. I'm rounding with that 5. That's 5 or greater. I'm going to add 1 to the preceding digit. 1.964 grams per liter of carbon dioxide. That is the density of carbon dioxide at STP conditions. Standard temperature and pressure. That's what STP conditions are, standard temperature and pressure. All right, we got one more problem to do. Let's give this one a try. If you have 0.0025 moles of oxygen gas at 1.1 atm and 25 degrees Celsius, what is the volume in liters? So the question is, do I have two pressures? No, I got one pressure. Do I have two temperatures? No, I got one temperature. Do I have two volumes? No, I'm actually asked to solve for a volume. So since I do not have two of anything, I am not using the combined or general gas law. Consequently, I'm using the last um, uh, mathematical relationship that I had here on this, and that is the ideal gas law. That's PV equals nRT. What are we solving for? Volume. But I'm just going to plug right directly into this equation here. So hopefully you can do that as well. Okay. P is for pressure, and that is 1.1 atm. The V, the volume, I'm solving for that. The N is the moles of gas, and that was given at 0.0025 moles. And then we have the gas constant. We've used that in the previous problem. It's up at the top of this sheet of paper, and that's 0.0821 liters atmospheres divided by moles Kelvin. And then the temperature, and the temperature needs to be in Kelvin. So I'm going to have to add 273 to that 25, and that is 298. So 298 Kelvin, just like that. I am going to solve for this volume. So I'm going to divide both sides by 1.1 atmospheres, dividing by 1.1 atm. Just like that. This cancels out. This is looking good. Okay. And then I'm going to plug into my calculator. This is V that I'm solving for. And so V is going to equal, I'm going to do this right underneath my notation here. And I'm going to plug into the calculator 0.0025 times 0.0821 times 298 divided by 1.1, and I am going to get 0.055604. I'm going to round this to the appropriate number of significant figures. This has two significant figures. This has an infinite here, and this has three significant figures, and this has two significant figures. So I need two. That's one, that's two, that's six, that's five or greater. I'm going to add one to the preceding digit. That's 0.056. And this is liters of oxygen gas, and that's diatomic. That's why that is what it is right there. All right, fantastic. You have watched another exciting, awesome video by none other than the Crazy Hat Chemist. So I greatly appreciate your time. I greatly appreciate to all of those who are actually watching to the end of this video. I greatly appreciate that. I hope you have a fantastic day. And remember, this is the place to come for all your learning of chemistry. And let's zoom on out on this here worksheet, and you can see the whole thing. Have a great day. Talk to you later. Bye for now.